Hello.
Hi. Oh my God, sorry. That was a struggle.
Oh shoot. Sorry about that.
No, you're all good. I had to change browsers, like it wouldn't let me, like, I don't know. It was a whole thing.
Oh,
But yeah. Um, I wasn't able to go to your content review tonight.
oh no. It's
Um,
okay.
so I was wondering, this is so bad. Can you like go over hydrogenation, I think it's called?
Yeah, hydrogenation. So let's say um that we have an alkene like that, right? And we have H2 and some kind of metal catalyst. And the metal catalyst can be any of these three here. You could see PDC, you could see PT, or you could see rainy nickel. Right? Oh wait, I'll be right back, be right back. I need to get some water really quick.
No worries.
Okay, I'm back. So for alkene reactions, right? There are going to be different things that you look out for. So the things that you look out for are going to be, let's say, the stereoselectivity. So this could mean that the reaction could either be syn or anti-addition. Syn addition means that the two groups attack the alkene on the same side. So if one group is a wedge, the other group would also have to be a wedge. Anti-addition is when the two groups are anti to each other or opposite from each other. If one group is a wedge, the other group is going to be a dash. Another thing is regiochemistry. So where the groups are attached to. So something could be Markovnikov or anti-Markovnikov. Right. So the way I like to think about this is that for Markovnikov, the nucleophile is on the more substituted carbon of the alkene, right? For Markovnikov. For anti-Markovnikov, it's the other way around. The nucleophile is on less sub carbon. Yeah.
Wait, just to clarify, the
Yeah.
nucleophile is the one that oh, this is so bad. Like it has the lone
Yeah, it has
pair.
the lone pair of electrons, right. And we'll go
Okay.
over examples of that when we do other reactions.
Okay.
But this one here won't have any regiochemistry because the two things that are added onto the alkene here are just the hydrogens and they're the same group. Uh, where the mechanism, wait for this reaction here, this is always going to be a syn addition, right? Which means that when the hydrogens attack the alkene, both hydrogens have to be on the same side. So if we choose the hydrogen to become a wedge, the other hydrogen will also have to become a wedge, like that. Right?
Okay.
Here's why that happens, because let's say we have a metal like PDC here, and let's say the H2 comes like this, where one H is red, the other H is blue. Right? Um, the H's are just going to get absorbed onto the metal catalyst. And once the hydrogens are attached to the metal catalyst, we now bring in our alkene. So let's say our alkene is right here, and I'm going to say that this is a wedge dash. Well, no, that's it. That's it. Wait, actually, yeah, dash hydrogen. So let's say that this red hydrogen here attacks one side of the alkene. The one of the bonds of the double bond is gonna be attached to the metal. So what that's gonna look like is this right here. Right. So that's gonna be like that. And then now this carbon here is attached to the red carbon that attacked that carbon. We still have a blue hydrogen on this metal like that, right? Where this, you notice how this bond here, what used to be the double bond of the alkene right there,
Yeah.
that bond there locks this alkene in place, this structure in place, where this blue hydrogen, when it comes back to attack the other side, and then that bond breaks onto that metal, it's forced to attack on the same side as the red hydrogen was. So if it was a wedge, then that hydrogen would also have to be a wedge. If it was a dash, the hydrogen would have to be a dash. But in this case, they're both planar because that alkene was locked into this place where when the blue hydrogen attacked, it had to attack on the same side as that red hydrogen, which is why this reaction is syn addition,
Okay.
right? And
So
uh-huh.
we kind of like break the double bond.
Yeah, we break the double bond and we add two hydrogens to it because you know how this double bond here only had one hydrogen on it?
Yeah.
Let's say that that one hydrogen was blue, and then the new hydrogens, the new set of hydrogens is red. That new set of hydrogens came from the H2 here.
Okay. And then they're always going to be on the ends of the alkenes.
Yeah, they're always going to be on the end of the alkenes, on the carbons of the alkenes.
And then how do we know, like, for example, the blue ones in the first, in the reactants, we don't know if, well, it's planar. So how do you tell if like the ones you add are going to be forward or like up or down?
Yeah, yeah. In this case, right, it doesn't matter. The red uh could have been a wedge, which I did in this case, or it could have been a dash, right?
Okay.
In this example, there are examples where it does matter, and I'm gonna show you that those examples now. Okay. So let's say we have something like this, and instead of having H2, right, you could see D2. That's just an isotope of H2. This is deuterium ion. The reason why professors write that sometimes is because they want you to draw out the stereochemistry. Because you could just say like your answer is this without drawing in the hydrogens because you know how hydrogens are invisible. We could say that that's
Yeah.
implied. If the professor wants to test you on the stereochemistry on this, then they would put D2 um where you have to actually draw out the deuterium ions. You can't say that that's invisible, right? Where
Okay.
you notice how there are two hydrogens here already.
Yeah.
Um, which side do you think the deuterium ion has an easier time attacking, the top side or the bottom side, based on what's around the molecule?
Bottom,
Yeah, the bottom side, because the top side here, you notice
a
how there are
wedge.
two wedge bulky butyl groups.
Yeah.
There's too much steric hindrance on the top side blocking the deuterium ions. On the bottom side, there's more space for the deuterium ions to attack. So the deuterium ions will attack on the bottom side like that.
So deuterium ions do care about regioselectivity, but the hydrogens don't. Or
Um,
the one we did before.
uh-huh. Well, um, it depends on the molecule. In this case, it doesn't. Like, let's say we had a hydrogen like H2. These H2s will still care about the regioselectivity. Like that would still be a dash like that. The green H's,
Oh,
they will
okay.
still go back. But you don't have to draw those H's out on the exam. You can say that's invisible.
Yeah. So
But
it's not dependent on the reactant, it's
mm,
dependent on the starting molecule.
yeah, uh-huh.
Okay, got you.
Yeah, yeah.
Okay.
But yeah, uh-huh. Now let's see. What other thing could happen? Oh, another thing that could happen is that let's say we have um and we have H2 PDC. So you know how we're gonna add H's on all of these carbons here that are double bonded?
Yeah.
And then
We,
they could
we
uh-huh.
oh sorry, we always add them on. Wait, but we only have two hydrogens.
Oh yeah, think of them as an excess. Like they are going to be in excess. Like think of it as gas. There's a lot of them
Okay,
in the reaction,
gotcha.
right? And you know how when we add them onto the alkenes, it doesn't matter if we attack it on the top side or bottom side because like there's no other bulky groups that are wedge or dashes.
Yeah.
And you know how we include wedges or dashes on chiral centers only? Let's say that we get rid of all of the double bonds here, right? Which carbon here is the chiral center?
The one with the methyl,
Yeah,
right?
that's right, right. Uh-huh. Because that carbon there is the only one that has four different groups. This carbon here is not a chiral center because they have two of the same groups, which are the two methyl groups, right?
Gotcha.
Where that one chiral center there is really important because let's say the hydrogens were attacked on the backside. That forces the methyl to become a wedge like that, right?
Yeah.
But we also could have had the hydrogen attack on the front side, making the methyl a dash like that, right?
Okay.
And you notice how that only one chiral center changed? Like, let's say this is one, two, one, two. This is one, two, three. This is R. This is gonna be S. If only one chiral center changed, and that's the only one we have, are these, what are they to each other? Are they identical? Enantiomers, diastereomers, constitutional isomers, meso?
Oh gosh.
It's okay.
Diastereomers?
Huh?
Or wait, but it needs two chiral centers.
Yeah, so diastereomers is when some chiral centers change and some stay the same.
Yeah.
Enantiomers is when all of the chiral centers change.
Oh, and
Right?
that can be one chiral center, right?
Yeah, that could be one
Okay, so
chiral
it's an
center.
enantiomer.
Yeah, that's right.
Gotcha.
These
And
are
oh, sorry, diastereomer has to have a minimum of two.
yeah, a minimum of two. That's right. That's right.
Okay,
Uh-huh. Right, right. It can have three, four, five, but a minimum of two. That's right.
gotcha.
Mhm.
Okay.
And there is no preference here because you notice how nearby there's no like bulky group or anything. So let's say the mixture between them is 50. If there's a 50-50 mixture of enantiomers, do you remember that specific name? Called
Racemic.
yeah, racemic mixture. If there's a 50-50 mixture of two enantiomers. Right? But you could have things that are not 50-50, like if there was a tert butyl here that is wedge, then which one do you think is gonna be your stable,
Major.
yeah, major one? Uh-huh.
The top one, because it's
Yeah.
gonna do backside attack. Or
Yeah.
anti, right?
Um,
Is that what you call it? Anti?
we call it like the backside. We don't call it anti-addition because anti-addition would mean that the two hydrogens are opposite from each other. Like if one hydrogen is dash, the other
Oh,
hydrogen has to be
okay.
wedge. There's syn
Gotcha.
addition because they attack on the same
Same.
side, right? Which the double bond is right here. Right. Yeah.
What if the methyl What if the methyl was back, or yeah, back, and the tert butyl was like the wedge? Like if it was the methyl was the dash
Oh, this
and
methyl here.
the tert butyl stayed the wedge, would
Uh-huh.
that be anti because you'd have one, the hydrogens would be opposite?
Yeah, so this methyl here cannot be wedge or dash because it's sp2 carbon. Um,
Oh,
like this sp2 carbon here is always flat. There's no wedge or dash possible on sp2 carbons.
wait, so how did we get um on the product wedge and dash? Because it's a chiral center?
Yeah, because this is a chiral center here where you know how the two H's, one H is attack on that carbon, the other H attack on that carbon on the same side, syn addition.
Yeah.
It would attack on the backside because of this wedge here, which is why we see two dash hydrogens on these two carbons of the alkene here. When
Okay.
the hydrogen attack on the backside, that forces the wedge, that forces the methyl to become a wedge,
Got you. Okay.
right? And the other one is when the two hydrogens are wedges, which forces the methyl to become a dash.
Yeah. And that would be the minor product.
Yeah, that would be the minor product. That wouldn't be a 50-50 mix of enantiomers anymore. And now this wouldn't be a racemic mix anymore. Right?
Okay.
And now this right here is a diastereoselective reaction because these two are diastereomers of each other now. Because now we have two chiral centers where we see that this chiral center here that reacted changed, but this chiral center here did not change. It stayed the same.
Oh, okay. Got you.
And we
So
said,
there would also be an enantiomer stereo. I don't know how you say it. Like, would it be an enantiomer version of stereoselective?
oh, enantioselective.
Oh,
Um, this is
yeah.
not going to be enantioselective because of these diastereomers here. This reaction is only diastereoselective.
Okay. Okay.
Uh-huh. Where it's selective for this diastereomer right here, the major one, that one that is less steric hindrance.
Okay. Got you. Because one changed and one changed or stayed the same.
Yeah. Well, these are diastereomers, but this is the major one because you know how the hydrogen prefers to attack the less sterically hindered side, which is
Yeah.
the back side. Yeah, that's why this is the major one, and it selects for this diastereomer. The
Okay.
reaction prefers this diastereomer because it goes through a more stable intermediate.
And then hydrogenation is always H2 or D2.
Yeah,
Would
always H2 or D2 with some kind of metal
okay.
like PD, PT, or rainy nickel.
Okay. Not too bad. I feel like Moscow made it a little more confusing.
Oh yeah.
Okay. Neat. Okay. All right. I know I missed I know you went over it because I was looking at your like outline, I guess.
Yeah, yeah. We could go over it again if you have like questions on it.
Okay, yeah. I really want to do Levens's practice.
Oh yeah, yeah. The chapter 11 and 12
Yes, she
reactions.
has like
Yeah.
3 pages on that. So
I
I was like,
know.
that would be really good.
Pascal didn't finish the reactions there yet. Like he just went up onto oxymigration, demigration, hydroversion, oxidation. He didn't do the radical halogenation, hydrohalogenation, the peroxide reactions, oxymigration, demigration. Oh no, the ozonolysis, the dihydroxy reactions yet. So he didn't, that worksheet can't be fully completed yet based on Pascal's
Okay.
thing
I
lecture.
just feel like he's gonna go over like all of that tomorrow.
Yeah, yeah. I
Like he's
think he'll
gonna
go over that
cram it
tomorrow.
in. Like
Yeah. The
oh
midterm is
my
on
God.
Tuesday or Thursday?
I think Thursday.
Oh, Thursday. I see, I see. Okay, okay. I'm not gonna show up on Thursday then.
Oh
If I
my
show up,
gosh,
I'll
yeah,
be like,
no.
I was like, oh, I took the exam. Write my name as
Oh my God. Well, you could. Why not? Like just
Yeah.
but yeah. Um Yeah, would you actually mind going through like some of the other reactions? Like I scheduled an appointment with you on
Yeah,
Friday.
yeah. I
So
saw. Did you
I
reschedule it to like
yeah,
4:50?
yeah, I'm so sorry.
No, 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 it's okay. It's okay. I saw it. I was like, but
Oh
it's
my
okay.
God.
I'm free. I'm free that time.
Okay, cool. Sorry about that. But
No, no, no.
yeah.
It's okay. It's okay.
Yeah, I was hoping that like I'd learn how to do the reactions and then do some
And then
practice and then the questions I have then Friday. You know what I mean?
yeah, yeah, yeah. So then we could go over like those questions that you have. Yeah.
Yeah.
Let's see. Let me pull up the outline. Okay. Yeah, I gotta post the notes too after this
Oh, no
to the kids.
worries.
Uh-huh. Let's see. What's next? Oh, okay. Addition of HX, hydrohalogenation.
Oh, oh, I meant to ask, is that the same as like the tape? Well, I know ours was alkanes last quarter, but
Uh-huh.
could like the table you did last quarter still work?
The table last quarter, HX alcohol. Oh, so that would not work because the table last quarter I made was for alcohols. Um, that is not gonna work because the thing we're working with this chapter are alkenes, right?
Oh,
So
okay,
it's a
yeah,
whole different thought process. But let's go over that logically, like right now, and how to do those things.
okay,
Okay. So now, oh yeah, yeah, I forgot for hydrogenation stuff as well. Like we just went over the reaction, right?
yeah,
Another type of question that he could ask you is ranking the different types of molecules, alkenes, by heat of hydrogenation. So what that is that you know how when we do this reaction, the double bond disappears, and then we add two hydrogens or deuterium ions onto the structure, right?
yeah,
This reaction here is overall exothermic, and it gives off some kind of energy, some kind of um yeah, energy.
because we broke the bond.
Yeah, because we broke the bond,
Okay,
right? Uh-huh. And the more stable the double bond is, right, the less energy it has, which means that when we break open a stable double bond, it gives off less energy. If we break open an unstable double bond, it gives off more energy. So the stability of alkenes can be looked at in three different factors. You could look at the hyperconjugation or the substitution of the alkene. So that's gonna be like this chart right here,
okay, yeah,
where you notice how the more substituted the alkene gets, the more stable it's gonna be.
yeah,
Wait, actually, let me just not. Wait, actually, yeah, yeah. Let me do that, and then let me just label this air things as like stability arrows, right? Because um the more R groups there are around the alkene, the more hyperconjugation it has, which is why it is more stable going from left to right. In this case, right here, stability,
yeah,
right? But the other arrow could be this right here, where we said that the more stable something is, the less energy it has. The less stable something is, the more energy it has. So this one right here, that is the most unstable alkene, has the most amount of energy because it's the least stable, right?
okay. So it's inverse.
Yeah, they're inversely related to each other. Energy and
Okay,
stability are inversely related to each other. Where this is talking about energy, right? So it also depends on what kind of question the exam is asking you. Like if they tell you to rank the molecules in terms of energy, or in terms of stability, they're gonna be like directly opposite from each other.
okay,
Right? So let's see. Let's talk about also that's one of the things. The other thing is conjugation or resonance, right? So which one of these systems do you think is gonna be more stable? Which one can do more resonance?
um, the first one,
Uh-huh. Right. The first one because they are adjacent to each other, whereas the second one here, there's an sp3 roadblock blocking resonance.
Yeah.
Right? So that means that this first one here is more stable. And does that mean it has more or less energy?
Less energy.
Yeah, that's right. Less energy. So that is a thing to look out for. Less energy. Less energy means more stable. More stable means less energy, vice versa. Less stable. And this is more energy. Okay. Another thing that you can see is E versus Z, where say we have that versus that. But actually, let's just say cis and trans because it could get, yeah, I'll show you why it can't be easy all the time. Cis versus trans. Which one is more stable?
The trans, I
Yeah.
think.
Uh-huh. So this one, since it's more stable, it will have less energy. This one will have more energy.
And geminal has the same energy as cis,
Yeah.
right?
Uh-huh.
Okay.
Geminal, same energy as cis because same stability as cis.
Okay.
Right? The reason why E is not always more stable than Z is because of some examples like this. Say we have, well, first, why is this more stable than this?
Less steric
Yeah,
hindrance.
yeah, that's right,
Yeah.
that's right. Less steric hindrance. We see the cis, the two groups are sterically hindered. They are right next to each other. Whereas the trans, they are across from each other. But now let's say we have, okay, oh yeah. Okay. So this right here, like if we make a dash line through the double bond, we look at this carbon, we know that the chlorine has a higher atomic number than carbon, which is why that's a higher priority group. Look
Yeah,
at the
and
other carbon.
bromine.
Yeah, this is Z.
Yeah.
Or wait, that's not the point I'm trying to make. That
Oh,
would be actually less stable than the trans version of it. Um, huh. Whoa. Wait a minute. Whoa. Wait. Z. Let's see. Is this always the case then? Hmm. Oh yeah. Okay, actually, yeah. Let's say we try this, and then we have E, because let's say that this right here is going to be, yeah, actually, you could say that E is always going to be more stable than Z. Yeah.
you will always. So it follows cis and trans.
Yeah, uh-huh. Cis and trans. Trans is always more stable than cis. E is always more stable than Z.
Okay.
Trans more stable than cis. E more stable than uh Z. Well, these arrows are talking about stability here, not energy. If it's energy, it's gonna be the other way around.
Okay. Yeah.
Stability. Okay. Another thing that you could see is ring strain. So let's look at these rings here. Okay. You notice how these carbons here are sp3 hybridized?
Yeah.
Since they're sp3 hybridized and a tetrahedral, do you remember the preferred bond angle they prefer to be in?
Oh, no.
That is going to be around 109.5 degree.
Oh, okay.
Uh-huh.
Yeah.
Right. Where if it's in a cyclopropene, a triangle, that's forced to become a 60 degree. If it's cyclobutene, it's forced to become 90 degree. Cyclopentane is around like 107 degree, and then cyclohexane, especially in the chair form, is around 109.5. Where the bigger the difference between the bond angle something is and its preferred bond angle, the more ring strain it has. So ring strain increases from right to left in this case because of the difference in the bond angle, actual bond angle, and the preferred bond angle. 60, the difference between 60 and 109.5 is bigger than the difference between 90 and 109.5, which is why cyclopropene has a more ring strain than the cyclobutene. Right?
Okay.
And if that's the case, that means that energy will increase from left to right. Ring strain and energy, I mean stability. Ring strain and stability are inversely related. Stability.
Okay.
Because the less ring strain you have, the more stable you are.
So ring strain kind of follows energy.
Yeah, Ring strain is going to be directly proportional to energy. So as you increase ring strain, you increase energy as well. As you decrease ring strain, you decrease energy as well.
Okay.
Ring strain and energy are inversely related to stability.
Okay.
Okay. So now let's do some practice problems where we are going to rank the following molecules in terms of um the heat of hydrogenation. Not stability, but heat of hydrogenation.
Which is energy.
Yeah, energy.
Okay.
Energy that it gives off when it's reacted with H2 metal catalyst. Okay. And then let's say one is gonna be the highest heat of hydrogenation or energy, and then five is gonna be the lowest heat of hydrogenation.
Okay. Um, the first one is one.
Is the first one gonna be the most stable or the least stable?
Or wait, resonance gives
Uh-huh.
more stability.
Yeah, resonance gives more
Oh,
stability.
okay.
Uh-huh.
So that would be five.
Yeah, yeah. It is the most stable, which means it has the least energy, right? But if the
Okay.
question was asking for most stable, then this would be number one. If the question was
Okay.
asking for the most stable, but it's asking for the most energy.
And I chose that as opposed to a different one because it had more double bonds. Is that the
Yeah,
way to
more double
go
bonds
or?
that can do resonance. Yeah.
Okay.
Right.
Um, are there some that are the same energy?
No, no, all of these are gonna be different, right? So
Uh, I'm
let's
between like the
uh
second one and the last one.
yeah, yeah, that's good because you know how these ones here can't do resonance at all.
Yeah.
So now they have the same amount of double bonds that could do resonance, right? If they have the same amount of resonance, then we look at the next factor, hyperconjugation. Which one of these systems has more double bonds that are more substituted?
Oh, the last one.
Yeah, because the last one has two di-substituted double bonds, whereas this first one here has
Oh, it's
one.
mono substituted.
Yeah, this one is
Gotcha.
mono, right? So this is gonna be four. This is
And
gonna
then
be
three.
three.
And then, okay, and then two and one in from left to right.
Yeah, you got it. That's right. Uh-huh.
Oh my gosh.
Let's do
Okay.
another set. And then I'll give you an extra set that I did not put in the content review session because I just
Oh,
realized
thank you.
that I just realized the fact there that today right
Oh,
now.
okay.
Yeah.
Um, okay, so this one is ring strain, right?
Um
Or
so
is
they're
this still
the
the
same
double?
size of ring, so it's gonna be very similar to this property here. It's gonna be about conjugation and hyperconjugation, resonance and substitution.
Okay. Um, oh, the third one is number 5, right? Yeah,
Oh, are you saying that this is the most stable here?
that's the, yeah, most
Uh-huh.
stable.
So you know how only two double bonds are doing resonance with each other? There's a system that has three double bonds that are doing resonance with each other.
Oh, the first one. Oh my gosh. Yeah, I
Uh-huh.
didn't see the top.
Yeah,
Okay.
yeah. The one outside the ring.
Yeah. Okay. So because, okay, more double bonds.
Yeah.
Okay.
That are resonating with each other.
Yes. And then would come, wait. Yeah, then the third one, right? Because it's tri-substituted as opposed to geminal and cis.
Yeah. Then the third one is number 4.
And then the second one,
Mm-hmm.
and then the last one,
Uh-huh.
and then yeah.
Yeah, you got it. Nice, nice, nice. Uh-huh. Okay, now this is the one where let's see. We kind of went over this earlier today, but I think you see like what I'm trying to do here. Let's say yeah, this is kind of the most obvious one then. It's like, yeah, let's see. Okay, 1, 2, 3, 4, 5
Okay. So the triangle
is going to
have
be
more energy, least
yes,
stable.
yes, most energy, number 1. Uh-huh.
I don't know the names, but the square,
Yeah, yeah,
do you know what I mean?
yeah,
Like
yeah,
now we're
yeah,
on
yeah,
to 5 and then 6 and then 7.
yeah, yeah, yeah.
Pentagon, hexagon. Yeah.
But these two are 6 hexagons.
Oh, then the one with the least amount of bonds has more energy.
That's right. That's right. Yeah, that's it.
Oh,
Yeah.
cool.
Uh-huh.
Okay.
Yeah, this is probably the easiest to recognize. These ones are probably harder to recognize, like the conjugation and hyperconjugation, resonance
Gotcha.
or substitution. Right.
Okay. Do you know by any chance if he's gonna release like practice exams soon?
I don't think
Or
so. I don't think he releases practice exams. He just says,
okay,
look at the textbook problems.
lovely.
Yeah. But I'll try to make one for you guys like by this weekend.
Oh my God, thank you so much. Literally
Yeah.
like the saving grace of this class. Oh
Yeah.
my God. Okay. Oh, also, my friend's trying to join your Zoom. I don't think she
Oh,
doesn't see a link.
she tried to join the Zoom or like through
Yeah.
the link that. Oh, I see, I see, I see. Uh, approve, approve. Okay, okay. They should get in now.
Okay.
Yeah, yeah. Because I gotta like approve for some reason.
Oh, okay. Yeah, she was asking if like you had to accept her
Yeah.
membership request. Okay, she should be here soon. But yeah.
Yeah. Okay. So
Mhm.
um these are also recorded too, so you guys can access the recording link for to review, and the notes will also be posted too as well on the website that you guys like sign up for. Like
Oh, okay.
there's a module for the recording links and the notes as well. Uh-huh.
Okay. Very
Yeah.
cool.
Uh-huh.
Thank you.
Yeah. So the next thing is the hydrohalogenation or addition of HX. Pascal says addition of HX, but it's also called hydrohalogenation, just in case you want to like look it up or something.
Yeah.
So before we go over that reaction though, let's go over some alkene stuff. That's gonna be very uh fundamental for all these reactions,
Okay.
right? So let's say we have this alkene right here. You notice how these two carbons are part of the alkene. Which carbon is gonna give you the most stable carbocation?
Oh, the one away from the the single bond. The
Yes, this one, right?
yeah.
Right. So that means that we want this carbon here to lose the bond rather than this one, right? Let's say that we could do resonance by moving that bond right there, which represents two electrons, onto that carbon right there, like that,
Yeah.
right? That means that this carbon here lost the bond, so that carbon would have to have a positive charge like that,
Yes.
right? And this is important because we do not want to do this kind of arrow because that would give us an unstable carbocation there, right? So this right here would not work because it gives us a primary carbocation, whereas this red arrow gives us a secondary carbocation.
Okay.
That means that this carbon here is the nucleophile that is going to react with the reactions that we're about to do.
Okay.
Okay, now let's go over the hydrohalogenation and the addition of HX. Okay. Oh yeah, someone else tried to join too. But then I felt bad because like I didn't I just checked now, like I got two requests, but I don't think,
Oh,
yeah, it's okay. They could join the next one.
it's okay. Yeah.
Yeah.
Oh gosh.
Oh, your friend's here.
Oh, okay.
Yeah.
Andrea.
Uh-huh.
Hello.
Yes, hello.
Hi.
Thank you for letting me in.
Yeah, no problem. Yeah, I was supposed to let you in like earlier, but I just like Camilla like reminded me to like let you in, so I
That's okay.
feel
Thank
yeah,
you.
yeah. So, let's say we have, let's do a simple example first and then build on the difficulty. We have that simple alkene and HX, right? X could be chlorine or bromine, usually. Let's say we have HBr. This HBr is a strong acid, so we have to look for our most basic group, which is this alkene right here. I'm gonna draw out the HBr like this, where we have one H and one Br there, and there's gonna be a bond between them. You notice how this is the carbon we want to have the carbocation?
Yeah.
That means that the other end of the carbon is gonna have the negative charge, because you know how when we do resonance, that carbon there is gonna have the negative charge, right? You don't have to draw that out when you draw the mechanism. Just draw the arrow from that carbon attacking the hydrogen right there,
Oh, okay.
right? And that will kick off the bromine here. Like once this carbon grabs the hydrogen, the bond between the hydrogen and bromine breaks off and goes to that bromine right there,
Okay.
right? So now, once we have done that, this hydrogen here that was grabbed is that hydrogen right there. This carbon here lost the bond, so that carbon there has a positive charge now. And this double bond here is now that bond between the carbon and hydrogen, because that double bond was moved to make a bond between that carbon and this hydrogen right here.
Yeah.
Right? And now once we get to here, we can now bring in the Br minus that got kicked out as a nucleophile to attack that carbocation right there.
Okay.
Right? And then once that happens, we are going to have a bromine right there.
Okay.
So now it could get more complicated because let's say we have something like this here. What is going to happen first?
The double bond attaches to the H, and then you get a bromine ion, right?
And which carbon grabs the H?
The end
Yeah, the end, because we want the middle to have
to
the
be secondary,
Mhm.
or the carbocation.
Yeah, we want the carbocation to be more stable secondary, right?
Oh, does this one do a hydride shift
Yeah,
or a
yeah.
methyl shift? Okay,
Right, right,
yeah.
right. Because whenever you form a carbocation intermediate, always look out for rearrangement. You got it. That was the trick.
Okay.
That is why this is harder than the previous example. Rearrangement. So it could be hydride shift or an alkyl shift or methyl shift, right? Where we see the adjacent carbons, it could become more stable at this position, where that position has a hydrogen, where we could move right there, doing a hydride shift. Right. Now we have a carbocation on that carbon. Now we bring in the Br minus to attack. We couldn't do it right away because that would give us the minor product because this is the less stable carbocation intermediate. We have to get to our most stable carbocation intermediate first and then attack that carbocation with whatever nucleophile we have, Br minus, Cl minus, or whatever reaction we go through. Right. But that's the
Yeah.
most common theme for most of these reactions. Always form your most stable carbocation and then proceed. Like don't forget the rearrangement step, like the hydride or alkyl shift.
If
Right.
it wasn't like an alkyl shift, um, how do you know you'd have to change the methyl? Like,
Uh-huh.
would the hydrogen, I don't
Yeah.
know. Yeah.
So if it was an alkyl shift, that would mean that it was, let's say we have something like this, HCl. Um, there is no hydrogen to shift. So the only option it has is some alkyl group, some methyl or something. Right? Where we see that this position here can be more stable for this carbocation, but that carbon there has no hydrogens at all. It only has methyl groups where we're going to move one of those methyl groups there, doing a methyl shift. Where that
Gotcha.
blue circled methyl group is that blue circled methyl group right there.
Okay.
Mhm. This carbon right here lost a bond. Before it had 4 bonds, 1, 2, 3, 4, but now it only has 3 bonds, and which is why it has a positive charge now, because it's missing a bond. And that is good because we came from a secondary carbocation to a more stable tertiary carbocation. And then the Cl comes in to attack that carbocation to give us this product right here, right?
Yeah.
A lot of people would say that this is the product right here. They forget about the methyl shift. They just attack the Cl uh, to the more subside, right?
Okay.
Because the rearrangement shift, which is the hydride or alkyl shift, is um the most like commonly forgotten step, right? So this is major, this is minor, because this goes through a more stable carbocation intermediate. This goes through a less stable carbocation intermediate.
Okay.
Uh-huh.
Oh, oh.
Yeah.
Uh, in lecture, he said something about like, or I don't know if it was him or Mariah Jones, whatever, but she said something that like when you do a reaction, you create a chiral center, you have to like do something, or I don't forget what it was. Like, I don't know if it was like a
Uh,
nomenclature or yeah, like you're creating new chiral centers. That's important or something like that. Or am I,
yes. I think I know because the
yeah,
reactions,
I don't know.
um, let's see. I'll try to explain it with this reaction here. Let's say, it's more important for the other reactions like addition of X2 and wait, actually, Yeah. I'll try to explain using this reaction that we just did right here. Let's say we have this, that, that double bond. No, yeah. And then let's say yeah, that. Okay. And then okay, yeah. Yeah, we could talk about stereochemistry for this one. So say HBr. What's the very first thing that's gonna happen here?
The mono or the alkene is going to attack the H on the non or not as substituted side.
Yeah, that's right, right. Not substituted side. And then kick out the Br.
Yeah.
Okay. And then we form our stable carbocation intermediate, where this is also tertiary, but it wouldn't want to do that because it's already in its most stable position. So it would rather stay here.
Yeah.
Right. This is less stable, so it's not going to move there. So now, you know how this is an sp2 carbon right there that is flat and planar?
Yes.
Flat and planar. The bromine minus can come in on the top or bottom side, giving a wedge or dash product. But there is a preferred side.
Oh,
And
the bottom
yeah,
dash, right?
yeah. The dash side. That's right,
Okay.
right. Because of this group right here that is wedge, it's blocking the bromine from becoming a wedge as well. There's
Got you.
stericangents on the top side. Right. You got it. You got it. Right. So if the bromine is a dash, that forces the methyl to become a wedge.
Oh, okay, yeah.
The minor product is if the bromine went on the top side where it was already bulky and stericangents blocking the way, that forces the methyl to become a dash. So this is major, this is minor. Right.
Okay.
So that's the stereochemistry of this. And also, what's the relationship between these two molecules here? Like, what's the stereochemical relationship? Enantiomer, diastereomer.
Oh, they're both flipped though, right? So an enantiomer.
This chiral center here is both flipped. We'll have
Oh,
another.
but one stays the same,
Uh-huh.
diastereomer. Yeah,
Yeah.
sorry.
Uh-huh. That's right. That's right. I think you were focused on the reacted one,
Yeah.
right? Don't forget about the other ones as well. Don't forget about the other like pre-existing chiral centers that are there.
Okay.
That does nothing because that yeah it's unreactive. Diastereomers. That means that you know how we have a major diastereomer and a minor diastereomer?
Yeah.
This reaction is then diastereoselective because it selects for one diastereomer over the other. One diastereomer is major over the other.
Oh,
So,
okay.
and he went over this in lecture, but a lot of people got confused about like the terms diaselectivity, enantioselectivity,
Yeah.
relative. But this is what it means. It's diastereoselective, stereoselective, because the reaction prefers or selects one diastereomer over the other. One diastereomer is major over the other.
Okay.
Diastereoselective, right? And you understand why, right? Like you understand why this is major and why this is minor?
Yeah,
Mhm.
because of the steric hindrance.
Yeah, yeah, that's right. Yeah. Okay. And this is also like he might also say relative stereochemistry because it is relative to this chiral center right here. This chiral center is the one that's changing. So that's why it's relative to that one. If that wasn't changed at all and it's absolute, right? Like we don't get uh any other mixed products and we just get locked into this one product here, then that would be absolute stereochemistry. But we could have a mix here because of this flat sp2 carbocation where the bromine can attack on the top side or the bottom side, which is why we have
Gotcha.
relative stereochemistry.
Okay. Very cool.
Yeah. Uh-huh.
Oh, last question. I know you said it's only bromine or chlorine, but what about iodine or
Iodine
iron?
can still happen, but it's not as common as chlorine or bromine. And Pascal said that it's like a little bit harder, but it's still possible. Iodine could still work.
Okay.
The
Gotcha.
HEC workshops like Mariah Jones and Edna Lamson, they use HI. HI would work.
Okay.
Right. HF would not work though. HF is too reactive and explosive.
Got you. Okay.
Yeah.
Neat.
Yeah. Any other questions on this?
Oh, I'm good. Thank you so much.
Yeah, no problem.
Yeah, I
Are
won't
you,
be able to go tomorrow.
uh-huh. Uh,
Sorry.
no, that's okay. I also like record the sessions, so like you could like access those as well.
Oh yeah, I'm
Yeah.
I'm watching all of them. Don't you worry about it.
Yeah, I also got like a mic because like I realized the recordings are kind of muffled when I walk away from my laptop because you know how I walk around the room
Oh
sometimes.
yeah, no, it's okay. I just
Yeah.
boost the volume.
Uh,
It works.
yeah.
But yeah.
Hmm. Sounds good. Sounds good.
Thank you.
All right
Yeah.
then. Thank you so much.
No problem. No problem. I'm
All
glad to
right.
help. See
Bye.
ya.
Bye. Thank you.
Bye.